In this session, we're going to answer some problems um, about integers. Okay, so let's start with problem number 1. So we're going to determine whether each of these integers is a prime. Don't forget, the prime number means the factors are 1 and itself. Okay, so we need to have two distinct numbers, 1 and itself. Okay, and to determine, okay, if there is other factor or factor based on the given. Okay, so we're just going to get the square root of the given, and then after getting the square root of the given, so the range to that we're going to do the divisor, the range of the divisor that we're going to divide to our given will be from 1 to less than square root of the given. Get all the prime numbers from that based on that range, 1 to less than square root of n. Okay, less than or equal to square root of n. Okay, get all the prime number and divide it to the given. And if there is a result, okay, wherein the remainder is equal to 0, therefore that number is not prime. Okay, but in case every time you divide a prime number from based on the given range, okay, all are not equal to 0, the prime number is the given is a prime number. Okay, so let's start with number 19. Okay, so what is square root of 19? So it's around 4 point something. Okay, so it means the range will be 1 to 4. So 19 divided by 1 is 19. 19 divided by 2 is not, so we have remainder is not equal to 0 when we divide 2 to 19, same as with we divide 3 to 19. 4 is um not part of 19. We're not going to divide 19 by 4, okay, since it's not a prime. Okay, so we're going to divide it by 1, 2, and 3. Okay, so when we divided it, the result is remainder is not equal to 0. So therefore, 19 is a prime number. Okay, how about 27? Get the square root of 27. The result is 5. Okay, so 5 point something. So the range will be 1 to 5. So let's divide 27 by 1. The result is 27, definitely. 27 by 2. The remainder is not equal to 0. 27 divided by 3. The remainder is 0. Therefore, 3 is a factor of 27. Okay, therefore, 27 is not a prime number. Okay, how about 93? Okay, get the square root of 93. It's 9 point something. So therefore, we need to divide 93 by 1, 2, 3, 5, 7. Okay, those are all prime numbers from 1 to 9. So definitely divide by 93 by 1, the result is 93. 93 divided by 2, the um, the remainder is not equal to 0. 93 divided by 3, the result is 31. Therefore, 3 is a factor of 93. Therefore, 93 is not a prime number. Okay, how about 101? So let's get the square root of 101. The result is 10. Am I right? Okay, so from 1, 10 point something. So from 1 to 10, we're going to divide by 101 by 1, 2, 3, 5, 7. So divide 101 by 1. So remainder is 0. Divide by 2. We have none equal to 0 as remainder. Divide by 3. Same. Not equal to 0. The remainder is not equal to 0. How about 5? Definitely not equal to 0. How about 7? Definitely not equal to 0. So therefore, this is a prime number. Okay, how about 107? Okay, so again, get the square root of 107, and the range will be 1 to less than or equal to square root of 107. Okay, divide all the prime number to 107. If there is a quotient equal to 0, that number is not a prime number. Okay, so this is a prime number. Okay, so when we divide 1, 2, 3, 5, 7, it yields to when we divide 2, 3, 5, 7. Okay, not including 1, 2, 3, 5, 7. Okay, the result is not non-zero remainder. Okay, so how about 113? 113. Okay, so again the range is 1 to 10. So still yes. When we divide 2, 3, 5, 7. Okay, the remainder is not equal to 0. Okay, again, so get the square root of the given. That will be the upper range. The result will be the upper range of the range of the divisor from 1 to less than or equal to square root of the given. Then get all the prime numbers of that range and divide it to the given. And if there is a remainder equal to 0, that number is non-prime. But if the quotient is non-zero, all non-zero, that number is a prime. Okay, so don't forget that. Now let's move on with problem number 2. Find the prime factorization of this integer, 39. Okay, so let's get all the prime factor. So 2, we cannot divide 2 to 39. It will not yield a remainder equal to 0. How about 3? Yes. So 39 divided by 3, it's 13. So 3 and 13. So this is the factor of 39. We're not going to check other factors. So at least get a pair. Okay. A pair that could yield 39. So this is okay now. So we're going to check if the factor are prime number. 3 is a prime. 13 is a prime. So therefore, this is a prime factorization of 39. So that will be our answer. Okay, how about 81? So definitely, okay, 81, one factor of 81 is 9. Okay, 9 times 9. So after getting these two factor, check if it's a prime factor. 9 is not a prime. Okay, so we need to get the factor of 9. So how are we going to get 9? We're going to multiply 3 by 3. So that's why I have 3, 3 here. Same as with 9 here, 3, 3. So as you can see here, all are prime numbers. So therefore, this is already the prime factorization. So we could rewrite it as 3 raised to 4. Okay, how about 101? This is already a prime number. So the result is just 101. How about 143? Okay, so we're going to get, okay, so we could apply the algorithm that we used to determine if it's a prime or not to get the factors of the given. Okay, so square root of 143, so 11 point something something. Okay, so from 1 to 11 divided by 143. Okay, and then afterwards, yeah. And then, so we found that 11 is a factor of 143, and the result is 13 when we divide 11 to 143. So therefore, this is the factor of 143. And then check if each factor is a prime number. If not, we need to get the prime factor of that factor. Okay, so 11 is a prime number. 13 is a prime number. So therefore, this is already the prime factorization of 143. Okay. Problem number 3. Which positive integers less than 12 are relative prime to 12? So basically, we're just going to determine, okay, from 1 to 11 if it's relative prime to 12. If it's a relative prime, so two numbers, the common factor is 1. That is relative prime. Okay, so let's start with 1 and 12. It's 1. Okay, and the GCD to 212, it's 2. GCD 312, it's 3. 412, it's 4. GCD 512, it's 1. Okay, GCD 612, it's 6. GCD 712, it's 1. 812, it's 4. 912, it's 3. 1012, it's 2. 1112 is 1. So it means that 1, 1, 5, 7, and 11 is relative prime to 12 since the only common factor is 1. Okay, the GCD is 1. So that will be the result of this problem. Okay, again, if it's a relative prime, the GCD is equal to 1, or the common factor is just 1. Okay, now let's move on with problem number 4. Determine whether the integer in each of these sets are pairwise relative prime. So we have 21, 34, 55, 14, 17, 8. So if say pairwise relative prime, so we're going to pair the given. So how many combination from 3 given? So we have 3, 21, 34, 21, 55, and 34, 55. And check if each pair is relative prime. If one of the pair is not relative prime, so the given is not a pairwise relative prime. But if all pair is relative prime, it means it is pairwise relative prime. The given is pairwise relative prime. So let's check for 2134. So GCD is 1. Okay, because this is 217, and then the other is 3 and 7. Okay, how about 2155? Still, the common factor is 1. 3455. Still, the GCD is 1. Since all combination yields to GCD equal to 1, therefore, this given is pairwise relative prime. But for 14, 17, 8, so the pairs will be 14, 17, 14, 8, 17, 8. So 14, 17 yields a GCD 1. How about 14, 8? It yields to 2. Okay, so that will be the greatest common divisor between 14 and 8. Since this is not equal to 2, so we may not check the 17, 8. Okay, since it already failed. This based on 14, 8, the given is already considered not a pairwise relative prime since it's already failed in the combination of 14, 8. Okay, but just to check, 17, 8 is 1. Again, 14, 17, 8 is not a pairwise relative prime because of the GCD between 14 and 8. Okay, problem number 5. What are the greatest common divisor of this pair of integers? So instead of giving us the exact numerical value, this problem give us the prime factor of a certain numerical value. Okay, so for letter A, we have 2 squared times 3 cubed, 5 raised to 5th for the first number. For the second number, 2 raised to 5th times 3 cubed times 5 squared. For the greatest common divisor, okay, so we're going to get all the prime factor of the two given, and then get this the minimum exponent. Okay, so we have 3 prime factor 2, 3, 5. So for 2, we're going to check the minimum exponent So between 2 and 5, definitely 2 is the minimum. So the first prime factor that we're going to consider to determine the greatest common divisor will be 2 squared. Okay, how about for 3? Since this is equal, automatically it's just 3 cubed. How about 5? So we have 5 here and 2. So we're going to consider 5 squared. So the result will be 2 squared, 3 cubed, 5 squared. Okay, so this is the result of the greatest common divisor. So when you evaluate this, that will be the common divisor between these two given. Okay, so letter B, 2, 3, 5, 7, 11, 13. The first number. Second number, 2 raised to 11, 3 raised to 9 times 11 times 17 raised to 14. So we have how many prime numbers as a factor between these two? So we have 1, 2, 3, 4, 5, 6, and 7. So we have 2, 3, 5, 7, 11, 13, and 17. Okay, so let's consider all those prime numbers. Okay, so between 1 and 11 as exponent of 2, we're going to choose 1. Between between exponent 1 and 9, we're going to choose 1. 5 raised to 1, and this is non-existing in the second number. Therefore, the exponent of 5 here is 0. So that's why we have 5 raised to 0 here, since it's not part of the second given. Okay? Same as with 7, it is present here, but not present here. So therefore, we're going to choose 7 raised to 0. How about 11? They have the same exponent, which is 1. 13, it is present here, but not here. So therefore, we're going to choose the 0 exponent. Same as with 17, it is not present here. Okay, it's only present on the second given. So therefore, we're going to choose the non-present of 17. So 17 raised to 0 based on the given. Okay, so by removing the raised to 0, so this will be the prime factor of the greatest common divisor. So by multiplying this 3-digit, that will be the GCD of these two given numbers. Okay, so that will be prime number 5. So based on the given, based on problem number 5, we're going to get the least common divisor. So unlike in getting the GCD, so in LCM, we're going to get the maximum exponent of the given. Okay, so again, for letter A, we have 2, 3, 5 as the prime factor of the given. So again, maximum exponent. So between 2 and 5, maximum is 5. So we're going to get 5. Between 3 and 3, they are the same. So just copy. Between 5 and 2, 5 is the max. So get the 5 as your exponent. And this is the prime factor of the LCM. And again, if you're going to evaluate that, that will be the numerical LCM of these two given. Okay. Letter B. So same given as problem number 5. So again, get the highest exponent between the prime factors. Okay. So we have 2, 3, 5, 7, 11, 13, 17 as the prime factor of these two given. Okay. So for 2, we're going to choose the 11 exponent. Between 3, we're going to get the 9. And then between 5, this is 1 and 0 here. So we're going to choose 1, 7, 1, 7, 0. So this is 7, 1, 11, 11. So this is 11 raised to 1, 13. And it's not present here. So we're going to choose 13 raised to 1. And last, 17 raised to 14, which is not present here, the 17. So we're going to choose 17 raised to 14. So basically, this is the LCM of the given two numbers. So again, if we're going to multiply this, that will be the equivalent LCM, okay, the exact LCM for these two given. Okay, so that's problem number 6. Again, LCM, get the highest exponent. Now, problem number 7. Determine whether each of these integer is prime, verifying some Mercian's claims. So again, Mercian claims means a prime number is defined by n raised to p minus 1, wherein p is a prime number. And when we evaluate that equation, the n raised to p minus 1, the result should also be a prime number. Okay, so 2 raised to 7 minus 1. So the result is 127. Is it a prime number? Yes. Okay, when we divide 2, 3, 5, 7, 11, it's not a factor of 127. Okay, so therefore, this is a Mersenne prime number. How about 2 raised to 9 minus 1, even though 9 is not a prime number? So let's evaluate it and then check it later if the result is still a non-prime number. Okay, so the result is 511. Get the square root of it. Okay, and then based on that, so all prime number from 1 to square root of 511. So we found out that 7 is a factor of 511. Therefore, this is not a Mersenne prime number. It's not a prime number. Okay, so this is a Mersenne prime number, and this is not, since the result is not a prime number when we apply the formula, when we evaluate the formula. Okay, problem number 8. So find GCD of 1625 and this common multiple for 1625, and verify that when we multiply the GCD and LCM, it is equivalent to 1000 times 625. Okay, so let's get the GCD of 1000 first. So the prime factor for 1000 is 2 cubed, 5 cubed, and for 625 is 5 raised to 4. So therefore, the GCD is, okay, 2 raised to 0 times 5 cubed. Okay, again, why 2 raised to 0? Because it's not present on our second given. So we're going to choose 2 raised to 0, which is equivalent to 1. So 1 times 5 cubed, again, 5 cubed is the smallest compared with the 5 raised to 4. So that will be the chosen factor. So 5 cubed is equal to 125. So this is the GCD of 1000. And for the LCM, again, get the highest exponent, which is 2 cubed, and 5 raised to 4. The result is 5000. Okay, and then multiply these two. And is it equivalent to 1000 times 625? Yes. They yield the same product, 625,000. Okay, so therefore, this theorem, if you still remember, this is a theorem. So this theorem is correct. Okay, so that will be my last slide for this session. Okay, so see you on the next video lectures. Thank you for listening. So see you.